It's a little bit misleading. It talks about dynamical cores, but my real focus is the unified system of equations for the reasons that it is hard to understand sometimes. So I help all these organizations, and some of them help, some of them don't help, but I think that is the nature of the things. And also, I think I should thank the organizers for this great meeting. I think this is the best one that I have been in. And I also want to thank the person who invented this. What is this? So Apple would never do anything like that. I'll talk about unified system of equations. I will introduce them to you, and I will discuss the solution algorithm and what would a normal mode analysis yield, and I will show some results from the dynamical course based on unified system that we are developing. And I will try to go this pretty quickly. These are, each one of them will be addressed. But if we look at the basics, is the unified system is designed to yield elastic solutions for quasi-hydrostatic motion and unelastic solutions for non-hydrostatic motion. These sentences may not mean that much, but probably we will understand later. So it filters vertically propagating acoustic waves, and it does not introduce any approximations to thermodynamic and momentum equations. The continuity equation is the only equation that is approximated, and we will see what that approximation is. And it doesn't need a basic state or mean state. It has a total energy equation, and it covers wide range of horizontal scales, and it is good for the global cloud resolving models. At least this is our main purpose. So unified equations are available almost in all of the coordinates that we know, and it can be really added on a current hydrostatic model like sigma model if you have. Now I would like to show the equations and what it does. Unified system has two: potential temperature and the height. These are unpartitioned variables, which means that they have hydrostatic and non-hydrostatic the components in them, and we cannot separate them. Though we can separate pressure and the density, so does the temperature. That is, I didn't include. And the definition is, this is the quasi-hydrostatic component, and this is the non-hydrostatic component. So we have pi. Pi is the Exner function, and this is the pressure. It is really related to each other with these equations. And we have two state equations. One is for the full system, one for the quasi-hydrostatic part. And each one of them sees the same potential temperature. So this is the thermodynamic equation. As we see, it is not approximated. And horizontal momentum equation is not approximated, although I wrote them in two components. This is not an approximation. This is just the definition. And if we are not familiar with this form, this is actually is 1 over rho grad P. So this density is not hydrostatic density. This is the density that we know. And in the vertical momentum equation, we divide this thing to two equations right here. And the first equation sees non-hydrostatic pi, vertical derivative of non-hydrostatic pi. And the second equation, which we will use to calculate pi qs later. So what we can see is the z that we see appears here, and also it appears here. These are the same z. So if they are non-hydrostatic here, they are non-hydrostatic here too. This is the continuity equation. This is the equation that is actually approximated. So it is only predicting, which is according to this, in real model, it's not used as a prediction equation, but it is it has a d rho qs dt, and the densities are here is the hydrostatic densities. Assumption obviously is the quasi-hydrostatic component is much larger than the non-hydrostatic component. So it turns out to be, ignoring only this term, the non-hydrostatic density dt equal to 0, or ignoring this term, is enough to filter vertically propagating sound waves. And in the discrete equation, we have to use, in the discrete system, we have to use this equation as a the diagnostic equation, so that we do not use really Richardson equation. I don't know if everybody is familiar with Richardson equation, but what Richardson equation does is it predicts density and it predicts potential temperature, and it says these two predictions has to match to each other because of the state relation, and then it finds a W matching them. We think that it is a very cumbersome way of doing it, so we avoid Richardson equation in the unified system in the height coordinate. So the next one is an additional equation. So far what we showed, the previous one, what we show in these three transparencies are the equations of the system. But what we do not have here, an equation for the non-hydrostatic pi. So that equation is obtained from the three other equations from the previous transparencies, which is vertical and horizontal momentum equations and the continuity equation. So what this does is it puts all these non-hydrostatic x-nar terms to the left-hand side, and to the right-hand side it puts the terms that is basically quasi-hydrostatic and velocity. So this is every time you have to filter something, you end up with an elliptic system. Notables about this is that, first of all, this term on the right-hand side. So this is what we can see is the hydrostatic x-nar function. So it is the same term that appears here, but instead of non-hydrostatic, it is the quasi-hydrostatic component. So what that means is if there is a minimum of pi qs somewhere, this one is going to yield a positive, it's going to yield a maximum d pi in the same location. So they are going to, non-hydrostatic is going to try to compensate the hydrostatic part. And the second thing is this second derivative term on the right-hand side. We will see how we obtain that one. It's not very complicated. So when we have this additional equation, I call it new equation, what we have to do is we have to remove the already existing equation from the system. We cannot have equations doing the same thing. So what we do is we replace the vertical momentum equation with this. It is, I think, general practice in the anelastic equations. So the question is, why do we call this unified? There are a lot of word unified models, and unified prediction systems, and this is just a unified equation system. So if we replace this rho QS with the base value, basic state value rho 0, we obtain the unelastic continuity equation. And if we choose d pi is 0, our equation becomes quasi-hydrostatic system of equations. So it is the mixture of these two that unified system yields. So solution procedure is slightly different. Because of that, I have this order, and that how we solve. At least currently, it doesn't mean that this is the only way to solve, but I think this is good enough. So first, we provide the prognostic variables, theta and velocity, and these surface pressure and the pressure at the top, which is needed for the z coordinate. These are all secondary prognostic variables obtained from these ones. And the initialization, I start with w is 0 and d pi is 0. And then I have to, from this equation, with the w is 0, from the continuity equation, I obtain d rho qs dt for the start. Now, in the first step, we predict the potential temperature by knowing velocity, potential temperature W, and the heating too. So you can use any fancy schmancy time integration schemes here, but I just use Adams-Bashford. It works fine. And now this part is, we spent some time for this. So at this point, now it doesn't look that impressive, but when we were doing this work, it was difficult. So in the second step, now we know potential temperature. So we integrate this equation upward, and we obtain the difference of surface pressure, surface external pressure at the surface and at the top for the next time step. Now what we do is, from this equation, by getting time derivative of this and integrating with height, we obtain another pressure values for the bottom and the top. From these two, we eliminate the values at the top, and we obtain the surface pressure for the next time step. If you fail in this, Lamb waves would have a horrible time to propagate. After knowing the surface external pressure, we integrate this equation again, and we obtain pi qs. And now we have pressure and potential temperature in the next time step. Then that means we can calculate density, and so does we calculate d rho qs dt. And from the previous value of d rho qs dt and this new value, we have second derivative of the density. Let's not forget that this rho qs dt is actually very small compared to horizontal and vertical mass convergence. If it is not large, something is very wrong anyway. So that is a minor thing. Then we solve our elliptic equation. So this elliptic equation is, notice that in the unelastic system, this is pi prime. So it finds a pressure, it finds a non-hydrostatic pressure, it finds a deviation of pressure from a basic state. Here it is finding a deviation of pressure from a local quasi-hydrostatic one. So it is actually doing much less work than the unelastic system. So this is counting downward, right? didn't work. So so these boundary conditions are necessary for to guarantee that this equation is consistent with the momentum equation and the boundary conditions that W remains 0. And after finishing this, now we can predict the velocity. And this is the scheme that maybe can be called poor man's implicit scheme. After you finish all the mass calculations, you use that in the pressure gradient force. It's a nice trick. And after that is the last move, is solving the continuity equation in a different way to obtain the W. This is what I was talking about, not to using a Richardson equation. So we know the request, the rho QSDT, and we solve this upward or downward. Doesn't matter, it gives the same result. If it doesn't, I think you should go and check the calculations again. So this is the how the unified system is solved in the z coordinate. In sigma coordinate, it is actually much simpler, but z coordinate is more attractive because we can make dispersion relations. And what happened is the what we are trying to imitate is the fully compressible system. So this is the frequency. This is the wave number, horizontal wave number. When you see 10 to the minus 4, this corresponds to 60 kilometer wave. So, and it goes to 60, 606 kilometers in this form. So blue ones are the gravity modes. Green one is the Lamb wave, and these are the different the acoustic waves based on different vertical wave numbers. So quasi-hydrostatic starts pretty fine, but the gravity waves start flying for the short gravity waves. Anelastic does pretty well. It's amazing, but this is because of canceling of two errors. We will see where the errors do not cancel. And pseudo-incompressible is pretty well, although there is a little bit of change of the very deep modes. And the unified has the same as inertial gravity waves of fully compressible system, but it has the Lamb wave too. So this is where the problem with the anelastic system, this is the phase angle, and as you can see, deep modes are having large errors. Pseudo-incompressible system fixes that